Oil pumps, standard, high pressure, high volume, full raceability goodness. What do they do and who cares? Well, we're gonna find that out this time on Engine Masters. You know, like 90% of the engines that we build are standard street strip muscle car V8s that used regular old stock type oil pumps. And the thing is, when you're shopping for parts, you always see the catalog says standard and high volume and high pressure. Every once in a while you'll get like, you know, high volume, low pressure, high volume, standard pressures, pressure, high, low, all sorts of mixtures of stuff. And I just never know what it really means. I just sort of, as a knee jerk, go to the high volume one. I don't even know why. What does it do? Well, we finally decided to find out for sure. And to do that, we bought 3 different types of stock replacement Melling oil pumps for big block Chrysler and also a Mylodon billet unit. The reason we picked the big block Chrysler, by the way, is it has an external oil pump right here. So we don't even have to drop the oil pan in order to make these changes. It's gonna happen really quick. However, I think that the sort of design criteria and thinking that you're gonna see from companies like Speedbro and Melling are gonna translate from this engine into, you know, small block Ford, big block Chevy, anything like that. And so what we're gonna see in standard, high volume, and high pressure probably carries through the product line. But specifically, here's what we're dealing with. The first one up here is the Melling M63, which is the standard pump. Nothing special about it. And then I got the Melling, what they call high pressure pump. And having like held these, taken them apart, looked at them, inspected them, it looks like the only difference between standard and high pressure has got to be what they're doing with the relief spring in the bypass, because the case and the guts of this thing are identical. Now, what's interesting is when I move on to the one that they call the M63 HV, high volume, all of a sudden things get a little bit different. If I hold them up right like this, you can see that it has a deeper case on the one that is marked high volume. Obviously, they're taking a bigger grab of fluid through the gears inside that pump simply by making the case taller. So those are my 3 Melling pumps. And then the other thing that we did is that we got a Mylodon billet pump. And not only is this like racier because it's billet aluminum, it's got the same case thickness as the Melling high volume, but a different design pump entirely. So what is this all gonna do? I don't know. That's why we're gonna throw it on Steve Dulcich's 440. It's making about 520 horsepower in its current configuration, so we're gonna be able to data log whether the different pumps actually eat more or less horsepower, which is something that you hear sometimes, is like, oh, the high volume or high pressure pump is gonna eat more horsepower. Is that true? The other thing we're gonna be able to look at is some data logging of the pressure and volume of the oil through the engine. And then we're gonna sit down with the Steves, look at their opinion on these pumps, run them on the engine, and look at the factors of power, pressure, volume, and who cares. All right, Steve, it's another 440 Mopar test, this time oil pumps. How do you feel about me running the standard volume, low pressure, regular Chrysler Imperial or Dodge Van oil pump on your 440?
It's perfectly fine because
really?
It's a, what do they call it? A G-rotor pump?
Yeah,
And it's just a positive displacement pump that moves a lot of oil. Even the stock one's plenty for most high-performance engines. In fact, I've run over 760 horsepower on my Engine Masters motor using a original stock pump that was just sandblasted inside and out.
To that point, do you actually think the standard volume pump makes more horsepower than the higher volume, higher pressure pumps?
In theory, you would think so, but how much horsepower does it really take to go from 50 PSI to 65 or 70? I don't know.
That's what we're here to find out. See how he just walked right into that?
No,
It's almost like he set up the show for us. So what temperature do you want to run the oil at for all of these tests?
You know, I think if we get it into the 150, 60 range, I think that's reasonable. As long as we're the same, it can be 130. As long as we do it the same on every oil pump. I'm thinking 150 is probably reasonable.
Yeah.
And after that, there'll be pretty much no rocket science. We're going to look at oil pressure, oil volume, and we'll be monitoring the temperature just to make sure that our testing is consistent. And of course, we'll also look at the horsepower and torque so that we'll know maybe if these pumps are actually eating power, if it's actually a window that we can actually measure and repeat.
Good question to answer, because how much does it really matter? I mean, is the whole window of high pressure to low pressure just 2 or 3 horsepower, or is it 10 horsepower? That's a big difference.
It's 2 or 3 is my guess.
Yeah.
But hey, we won't know until we try, which is what we're about to do. So I guess fire it up, warm it up, and we're gonna start with our standard, regular old low pressure, low volume pump.
Standard
Off I go.
Action Brulé. I kind of like that. It's like Action Jackson. Action Brulé. What did we learn just now? We idled it at 950 RPM and it had 31 PSI after the pull. So that'll be our routine each time, is right after the pull. Wow, so we made 540 pound-feet of torque, 523 horsepower. Let's have a look at the oil pressure curve. This is the oil pressure curve, which is kind of weird.
No, look at this whole scale is 2 pounds.
Oh, okay. I'm like, what's going on here?
It really revved it up here and picked up 1.5 pounds right here.
Yeah, so this right here is 52.75 PSI, and that's 54 PSI. Now the one that I really have no idea what to expect is flow in gallons per minute. Okay, 4.9 gallons per minute at peak, but once again, this scale is 4.5 gallons per minute to 4.9. So that's essentially a flat curve.
A couple of quarts there.
Yeah. Is there any other data that we need to look at? I mean, we've got idle pressure, we've got pressure at RPM, we've got horsepower and torque, gallons per minute.
We're maintaining, I mean, the temperatures, it's pretty tricky. I ended up making the run at 146, 151. I'm only gonna be able to keep it within 1 or 2 or 3 degrees. You know,
That's pretty
it's hard
good.
keeping them both that close. You know, what surprises me the first time I had done a test like this was how much oil that really is.
How much is it, Steve-O?
Well, it's 5 gallons. I mean, in a minute.
Per minute, yeah.
That's a lot of oil.
That's
when you look at the clearances
in 30
things.
seconds.
Yeah.
I guess we got nothing to do but go swap on what? We have an option of high volume or high pressure.
Well, I think the clear choice here is you take the high pressure pump and put that on next.
Yeah. We're gonna go put on the high pressure pump. Looking at power, Steve wants to say that it's an improvement. I want to call it the same.
I have to say it's the same. I mean, we're talking 1 horsepower to 520. It's like...
Yep. The power actually is now 543.1 pound-feet of torque, 524.5 horsepower, which is a very minor improvement on the range of 0.2%.
But you can definitely look at that data and say, it didn't soak up a whole bunch of extra power to run
It didn't
higher
make
pressure.
power, didn't soak power, exactly. So that's not the story here. The story is going to be much more about the pressure and volume. You already checked the idle pressure at 950 RPM?
Yeah.
And?
32. 32 pounds.
And we had 31 before, so that's
call
the
that the same.
We made 54 PSI at peak with the standard pump on the thing, and this made 75.9.
So it's regulated at a different pressure, basically, is what you can say about it.
And once again, in case you're freaking out at this curve, the scale here is from 74.9 to 75.9. So, I mean, from here to there is 1 pound. So the data, there you go. You compare the two with our older pump, with the standard pump, versus the high pressure pump, and you can see they're both flatlining all the way out. It's just you get 22 or 3 more PSI with the high pressure pump. How about the oil volume, gallons per minute?
It does flow more.
It flows more, 6.1 gallons per minute at peak. So our standard oil pump, we saw 4.9 gallons per minute at peak. And with the high pressure pump, it's 6.1. So it's flowing more. However,
After the bypass.
After the bypass.
Not before the bypass.
I bet you they're both flowing the same. It's just we can't measure it. This is kind of what I was getting to, because the extra gallons per minute are bypassing on the low pressure pump, and they're not bypassing on the high pressure pump. They're going through our filter where we're measuring it.
Yeah, more accurately, they're both bypassing. It's just the high pressure pump bypasses less.
Probably. You don't know that for a fact.
Well, yeah. That thing will make 100 PSI. It'll keep going up as RPMs go up. It wouldn't just stop at 75 and call it a day. It's just the spring opens at that point, and that's where that one's regulated at.
Yeah.
And really, all I wanted to get to, aside from all of the science behind it, is what does the pump do when I bolt it on the motor? Well, what it does is it makes more volume and more pressure.
Yeah. Well, I kind of take back what I said about I was perfectly satisfied with 55 pounds in the stock pump.
I like that better.
That rule of thumb of 10 pounds per 1,000 RPM, I think holds pretty true. This doesn't go to 7,500, but I'm a lot more comfortable with a flat curve of 75 than 55 in an engine like this.
Yeah.
Yeah.
Now we find out what happens when we do the advertised high volume pump. Did they mess with that so that it has more flow but more bypassing? But that's got to make more pressure, right?
If we're going to see a loss in power, I think it's with that pump.
That'll all become crystal clear in just a moment when we install it and go run it on the 440. As Brule returns, I'll give you the power numbers, which are 541.2 pound-feet of torque and 524.3 horsepower with that high volume pump. The horsepower and torque is the same in every single circumstance. So the data we really care about here is the pressure and the volume. Let's have a look at our data on pressure, I guess.
Okay.
First of all, we did our idling test at 950 RPM. Both other pumps were idling at 32 to 31 PSI. The high volume pump all of a sudden is idling at 48 to 49 PSI. Mm-hmm. So why would the high volume pump give us more pressure at idle?
Bigger gear.
Yeah, it's more volume.
It's a bigger pump. Mm-hmm. And so the other pump is requiring some speed to get it to that pressure to hit the bypass. This pump at a lower speed, because it's just physically bigger, is capable of making more pressure. But I believe it also hits that same bypass spring that the other pump has.
Right.
But it happens sooner.
Right.
Right.
So now you've got this really flat curve where it goes from 50 to 70 instead of 30 to 70 or 75.
And how about the pressure up at RPM? 75, 76. It's pretty flat curve.
Yeah, we're within a pound here,
Yeah, because I suspect that both of the high pressure and the high volume pump have the same bypass arrangement spring.
They must.
That's what I'm guessing. It's the same spring because one just gets there a little later.
Yeah. Can we compare the pressure curve of the high volume versus the high pressure to see if it affected the curve at all?
Now,
once again, our scale is not very much here. We're talking 73.5 to 76. So yeah, that's got to be when that relief valve opens. Yeah, and then it starts to recover.
But that's within production tolerances. I mean, essentially, I would call that identical results as far as most of the curve. It's 75 PSI.
Guessing if the pressure curve's the same, the volume curve's going to be the same too.
Well, one would think that those two kind of, you know,
maybe except for the very bottom of the. Oh,
For a
no,
given
we're starting
hydraulic
at 3,000 RPM, so yeah, it's going to be the same.
And there you go, they're identical because
Yeah.
the pressure
Yeah.
is the same.
Yeah.
If the hydraulic fluid's the same and the orifice or the engine passages are the same and the pressure's the same, then the volume's got to be the same.
particularly where we're measuring it, because we're measuring engine oil pressure
Right.
and flow and not oil pump pressure and flow. So
That's
those
what I
two
was
things
trying to
being
say
separate,
earlier, but I
know.
couldn't actually say. Yes.
Yeah, just to clarify that, because we're measuring at the back of the engine, so we're seeing what
The
the
engine
bearings
The
are
engine
seeing.
is seeing.
Yeah.
Yeah.
And it's interesting, you know, it tells me not to sweat over power losses.
No, there's
getting
no
a
power
higher
loss.
powered or higher volume pump.
If there is, I mean, you know, I've seen small changes before, but it was with big changes in pumps. It was like going from a small block Chevy pump to a big block Chevy pump. And that's a huge difference, and it was still a pretty small change.
But the
So-
question for me that's left actually is, I mean, this is all pretty straightforward. Why would you ever buy the high volume pump? Like high volume, high pressure, why did you buy one over the other
I'm
one?
kind of with you. The other one packages better. It's a little shorter. It's a little smaller. It's
Lighter.
probably less expensive.
Yeah.
I always used to shy away from high pressure pumps, and I'll be honest with you, it's because I didn't know.
Yeah,
I just
now we
didn't
know.
know how they function. This is good
Yeah.
information.
Wow, you guys did-
We always went high volume, but I have no problem whatsoever with 30 pounds of oil pressure at idle. I think that's more than adequate.
I like the higher oil pressure at bottom RPM.
Meaning
like
you would pick the high volume
every
pump
ti- every
because
time.
it has the higher pressure.
every time.
Yeah.
Yeah, hands down.
I guess the last one to test is the super trick billet oil pump. This is interesting because finally we've lost horsepower.
Yeah.
Maybe we hurt your motor.
I don't think so, David.
Hopefully not.
Maybe we'll find
No,
another
we're good.
explanation.
The power numbers are 538 pound-feet of torque, and the big one that we noticed right away was 516.8 horsepower, down from, 524.
7, 8.
Yeah, 7 or 8, which seems reasonable for maybe a power loss, but how come? What did the Mylodon pump do pressure-wise? We know that it made 43 PSI at 950 RPM idling, which as a comparison, we saw 31 to 32 with the standard pump and the high-pressure pump. We saw 48 or 49 with the high-volume Melling pump, and we saw 43 with the Mylodon pump. But how about up at RPM? We're seeing 80. Pretty consistently 78 to 80 PSI from the Mylodon pump. I think it's moving so much more volume, it's like cramming a bunch through the bypass.
Well, let's keep this in mind. The bypass and the cover is exactly the same unit that came off of our high pressure pump. So that hasn't changed at all. So what's in that pump body has to be responsible, right?
Well, we know that I don't know how to say it, gear rotor or gear-rotor design,
It's the same height.
same height, completely different design
We're
though.
talking clearances and how well the pump is built.
And it's a different shape.
It's a completely different.
Instead of having clover-leafed round doohickeys,
Okay.
it's more sort of swoopy triangle doohickeys.
It's a starship,
Yeah.
starfish.
It's a starship. It might as well be a star.
starfish. No, not a starship. A starfish style rotor rather than a clover leaf. It's completely a different design.
Okay, I didn't look at the gear, so the lobes are different shapes.
Yes.
Yeah.
So one lobe is obviously capable of making more pressure, and I have to believe that quality of pump The clearances and everything are way better. You know, the housing's probably more stable. There's a few things going on there. I noticed also it has a steel insert inside of the billet aluminum housing. So those clearances are probably very stable and very, very close.
And so therefore, even though it's flowing the bypass through the very same plate that we ran on the other pump, it's making so much more volume that it's either cramming a bunch more through there, it's doing something to eat more power because it's trying to cram more oil through the engine.
I think it's moving the bypass spring further downstream.
I forgot about the further option. That's right. We didn't think of that. We were talking about it when you were out here about how it was maybe the orifice size or something, but if it's pushing that spring more, that's a good answer.
Yeah, I mean, who knows what this pump is actually capable as far as volume and pressure. It's clearly really high up there.
You know, like I said, I'd seen it before in some big swings, like small block to big block pump, and I think we finally hit that spot here. And you know, off camera, we verified that there's nothing wrong with the engine and that it repeats just a couple of times.
Yeah, we ran it a few times to make sure this wasn't an anomaly.
Well, we were surprised. It's like, we better take a second look at this.
And so, what is the volume?
A little bit more, I would imagine.
Yeah,
not
6.6 to 6.7 gallons per minute, up from our high point of 6.1 to 6.2.
So more pressure?
Yeah.
More volume?
So you can kill horsepower with an oil pump.
You can. So see, all those guys that were doing it, we now can't call them chumps, as you would say.
Because it's actually true. You can kill horsepower. All right. Final conclusions on our oil pump episode of Engine Masters. I'm going to say, as a knee jerk, if I'm on Summit and I'm buying a pump for my new 440 build, I'm going to buy the high volume melling unit.
Oh, that's the one I like.
Yeah, I agree. Okay. There's no reason not to have the extra oil pressure at idle that is supplied by the high volume pump.
It's not costing any horsepower, so you might as well get the volume.
Yeah.
I agree, other than if it's touching a cross member or something, then I'm headed to the high pressure pump and skipping the stock pump.
And I also like the high quality and like ability to do other things with the Mylodon parts. I don't think I'm just going to buy it for an engine like this. It's kind of my average cruiser, but if I was doing something that I cared about more, if I was going to do external pickups, then I would absolutely have it. I have had it. I've had that Mylodon system on a couple of my Hemis in cars. Good times.
Again,
we'll come up with more fascinating, boring parts on future episodes of Engine. This time it's a Mopar muscle engine showdown with carburetors everywhere. We've got the 446 pack versus the legend of the 426 Hemi. Man, this is going to be really cool. As a Mopar nut, you're looking at everything that I dreamed of since I was like 15 years old. Over here, a 446 pack big block Mopar. Over here, the legendary 426 Hemi. When I was 19, I managed to buy a 4-speed 71 Roadrunner with a 446 pack. And way later, when I was working for Hot Rod Magazine, I finally achieved the dream of getting a Hemi in my 1970 Super Bee. The other thing that I did pretty much for my whole life is poured through car magazines and poured through books and later read through all the stuff in the Mopar message boards, and people have always had an argument. What is actually the better program, the 446 pack or the Hemi? You hear people say, oh, the 6-pack's way better on the street. The one that I love that I've heard all the time is, oh, the 426 Hemi loses its tune. It's just much more maintenance to have that engine. I don't know where that came from or why. But what we're gonna do here is find out the difference in power on the dyno. Horsepower, torque, who wins? What's the shape of the curve look like and why? So let me tell you what we've got going on with these two engines. These are not bone stock reproductions of factory specs. They're close. We got stock blocks, stock cranks, stock rods, but we do have forged pistons. We have stock cylinder head castings on both engines. And on the top of the 446 pack, we've got an Edelbrock aluminum intake manifold, just like what would have been used in 1969. Over here on the Hemi, the intake manifold is not completely stock because the original street Hemi intakes, like from say 1968 to 1971 type deal, would have had AFB carburetors on it. This is a stage 5 dual plane intake that has the pads for the carburetor spread apart a little bit so that you can run Holley carburetors instead of those early Carters. And then the big step away from stock that we took was the camshaft. We had Comp Cams make 2 different camshafts for us with identical lobe specifications. They're hydraulic rollers, and they've got 236 at 50 duration on the intake, 241 on the exhaust. The lift on the 440 is 549 on the intake and 541 on the exhaust. Now, normally with a 426 Hemi, they've got just a speck more rocker arm ratio than the 440, so with the same cam, they would have slightly more lift. This has a 1.5 ratio aftermarket roller rocker setup on it from Ray Barton, and so it's probably right at 1.5 to 1, so the lift is very close between these two. On both camshafts, we put them on a lobe separation angle of 108. So we're looking at 2 engines with identical camshafts. The other thing that varies just a little bit from stock is the compression ratio. This one has old TRW 6-pack forged pistons in it. We did the math on it, and it's right around 9.5 to 1. This engine over here also has forged pistons and reduced compression ratio versus what it would have been stock. It's right at 9 to 1 compression. So let me tell you the story of this 426 Hemi. It's actually a Mopar Performance crate engine, one of the very earliest ones when they first started reproducing these things right around 1994 and 1995. So it's a Mopar Performance block and cast iron heads. They're very similar, if not identical, to what you would have bought in a street Hemi back in the day. I've had this engine forever. As a matter of fact, it was used for mock-up purposes in the 1955 Chevy Gasser that Mike Finnegan on Roadkill has made famous as the Blasphemy. We used this to mock it up in that car. Unfortunately, it also got towed around all over the place, open without an intake manifold on it and full of dirt. So we appreciate NHRA Superstock racer Ken Etter, who went through this thing for us, cleaned it all up, put it all back together, and that's about the story of this thing, except for it's got a great future. It will be on Roadkill because we are finally building the Hemi Gremmy. Yes, an AMC Gremlin with that 426 Hemi in it. This might even be the first time that you've heard that that's official. Now, the 446 pack actually has background with Dulcich that dates back to when he was virtually a kid. So I'm gonna let him tell you the story of this thing.
The history on this engine really does go back to when I was just a kid, because where did I get it? I got it from under the hood of the 1971 Dodge Charger RT that I bought as a used car when I was just 16 years old. And it became the subject of my very first real engine rebuild, because I went out and spent hard-earned dough on a brand new set of pistons. I had it rebored, decked, crank ground, the whole 9 yards. Over the years, I experimented even with 2 factory stock, but completely clapped out 6-pack setups. I put gigantic cams in there. I learned to port heads before I even had a clue what I was doing on this very engine. So we're gonna take this thing, we're gonna run it on the dyno. I'm gonna finally see what it does against an actual 426 Hemi. And then I'm gonna put it where it belongs, under the hood of my 1971 Dodge Charger.
Pick a side.
I'm going there.
Okay, he's cheating because he's already seen this actually run, which concerns me, I have to tell you.
But I haven't seen that run.
Yes, you have?
No.
What?
No.
You pre-tested both of these.
Oh, yeah, well. If he can cheat, so can I.
He was a street racer back in the day, so I don't trust anything he says.
No, he's toying with our emotions here. That's what he's doing, Steve.
Pick a side.
Come on, man. I mean, that's a Wedge 440 against the Hemi. The
Right.
Hemi.
Cylinder head alone tells me
Well,
Hemi.
yeah, the Hemi's got to win. I mean, there's no question. The Hemi.
You look at this guy. Okay, I need to make an accusation. You ported these heads, didn't you?
No.
He actually had to pause and go, should I tell the truth or should I lie? And that in itself tells me.
Yeah.
No, honestly, these heads are 100% stock right down
Except
to...
for a little fluff in the bowl.
The OEM valves are in these heads from 1970. They're not even replacement stockers. They're a stock. And they're just off the shelf. I had them bolted on a stock 383 until recently. I pulled them off and, hosed the grease off of them and threw them on there.
So you're swearing this is legit?
Totally legit. I ran that on a completely stock 440 and a completely stock 383 for some magazine articles. And the 383 made right at 335 horsepower.
Which is what it was advertised as.
Yeah,
so.
And the 440 never made the 375 that it was advertised at. It made like 355 or something. So
anyway, our baseline here, or our very first test, is going to be the completely bone stock, with the exception of camshaft, Mopar 440 6-pack by Dulcich. Ready?
Got it. On the way.
This is not bad at all.
Told ya.
488.7 horsepower and the torque 525.1. That's pretty stout for what this is. How come?
Sure is.
I don't know. I think it's got a good cam in it, that's for sure. That hydraulic roller, I mean, it's 108-degree loop. I've run these exact same pair of heads on half a dozen engine combinations, and the most I've ever gotten out of them before is like 455.
You mean from any 906
Any combination, no, this exact pair of heads I used for all kinds of magazine articles back in the day. And
how much have you seen out of a 906 stock head?
well, that's the most I've ever seen.
This?
Yeah.
Huh.
I mean, I haven't tested like an ultra race engine that crutches the head, but I mean, for a basic street engine.
Weren't most of those other combinations that you could run flat tap at camshafts?
Yeah.
That's a big difference there.
The roller, yeah.
But is that the roller having a valve train problem up there?
Well, things get heavy, and if it's got a spring that was kind of originally set up for flat tap at pressures, if it's that exact pair of heads, then yeah, it's wiggling there just a touch. It probably could use a little more pressure.
Yeah, and let's not neglect the elephant in the room here.
What?
The six-pack.
That's the key?
Well, look at it. It's crowding 500 horsepower with the factory six-pack setup. So
It's pretty impressive.
It is pretty good. That was like 50-year-old technology.
So this was factory rated at 390 horsepower, but we've got headers and a much better camshaft. The question is compression ratio. What do you think those six-pack engines actually had from the factory for compression?
I've always found that they were kind of overrated, and I'd expect this to be somewhere in the upper nines, not really ever making the 10.5 it's advertised at.
But regardless, we all agree this is way above average for a stock head 440.
This thing is really amazing. I was quite surprised, after seeing what the single four-barrel stuff does. I now have a much greater respect for the six-pack stuff.
Oh, I don't think it's that. Because I think that I've tested that before, and I think you have too, and I think that the six-pack intake like this is roughly the same as a Performer RPM.
Yeah, as far as the factory intake. The factory iron.
Oh, it's factory intake?
Four-barrel
that's
intake.
a big difference.
I
That's
have a lot more respect for this six-pack.
But you agree this is about the same as the single four-barrel modern Edelbrock Performer RPM, right?
Yeah, well, I mean, it's right there with the best today's manifolds. Give or take a few horsepower here or there. Maybe some of the modern stuff, like a good RPM is a handful of horsepower better, like onesies, twosies, threesies, but
that's what I'm saying.
Yeah,
okay,
but not bad for the era this thing came out in. It's pretty hard to beat.
So bottom line, we're all really impressed with the 440. Now it's time to pull it off the dyno and roll in the beastly 426 Hemi.
Legend.
The legend, the elephant.
The elephant,
the beast.
king of the streets, the gorilla.
You know what's weird, Steve? Is
What?
I had completely sworn off Hemis and said that they were no good, and yet here I am, like, championing this thing.
Yeah. I've always wanted one, but it's always been too rich for my blood.
Man, it's so convenient to just be talking instead of working.
No.
Funny, I was just thinking the same thing. we know they are.
So either Brule is playing intense mind games with us, or this thing is a pooch.
I don't know. It must be an intense mind game.
I hope so, because the Hemi's got a lot to lose at this point. Can you imagine?
Well, there's no way.
There's no way.
No.
We got to see it run.
Yeah.
This is going to be our poll with the legendary 426 Hemi.
Well, Steve-O?
I hate you.
It wasn't mind games. I think there's more to the story when we start looking at it.
Oh, really?
Well, let's start looking at it then.
The Hemi runs in a little different RPM range, so we're going to have to kind of make some adjustments as far as looking at data.
So at a glance, I'm thinking that the Hemi didn't make nearly the torque, but we're about to pull up actual data. Well, here's our power peaks for the 426 Hemi. It made 513.8 horsepower, better than the 440, and 478.7 pound-feet of torque. Nowhere near as good as the 440.
Wow.
So let's look at the overlay and see how ugly this story really is.
Wow.
Interesting.
Wow.
Wow. So much different. Okay, this is stunning. We're looking at the 446 pack in red and the 426 Hemi in black. Wildly different for two engines with the same camshaft.
I know. That's what I was kind of alluding to earlier is they just, there's so much more to the story than just one's better than the other. I mean, it's almost like one's for one use and one's for the other use.
Man, it's crazy. It's not as apples to apples as some engine comparisons that we've done where it's exactly the same compression, exactly the same intake, exactly the same cam. The cam's the same. The Hemi has like half a point less compression, and intake manifold design and cylinder head design obviously wildly different, and look what you get.
Yeah.
And look at the interesting crossover point of where the Hemi overtakes the 440. Right at where the 440 is making peak horsepower RPM is where the Hemi is just ready to start pulling away. You know?
Wow. You know what? This is actually the lesson of what we've heard about these
That's
engines
what I was thinking
forever.
the whole same thing.
It is.
Yeah, like the 440 had all the torque at the drag strip and would just get out
Hemi's an
hard.
RPM motor.
And the Hemi would come on at the top end and reel it in.
And more basic than that, this is a lesson about two things. Smaller engine, 20 cubic inches less with the same camshaft, wants to rev more, and an engine with a giant cylinder head makes less low-end torque and more top-end horsepower.
Probably shorter intake runners too. So all of the things with the Hemi say, rev me up. That's what I want to do up there, and everything about the 440 says I want to make torque.
That is a crazy
Isn't that
difference in
amazing?
torque.
It's just textbook, the Mopar guy, like old myths that prove to be true, you know? The 440 torque is right there. I mean, that's a big,
This is what I was so excited to show you. And because I knew walking in there,
Right.
I had to turn the dial up to the Hemi. I've already been there with it. I had to go to 6,500 to see peak power.
Yeah.
With the 440, it was more like 57 or 800, you know? So to average them, I'm not quite sure how you want to do that. I was thinking about going from peak power 2,000 RPM backwards.
Because you would gear the car differently, obviously, and have different converter and everything else. Wow, this is actually really interesting. This is because the 440 has such a tiny, lousy cylinder head. It makes tons of low end and then runs out of air. The Hemi kills all the low end torque and then moves a lot of air at the top.
Yeah.
That's crazy. Here's another big question. What was the peak ignition timing for best power with the Hemi?
34.
less.
Yeah, 2 degrees less. I'm not familiar enough with the Hemi to say that this is right, wrong, but I know that I swung it both ways, and that's where it made the best power.
So ignition timing total 34 for the Hemi, and the best power was made at 36 on the 440. Just out of curiosity, because people always think the Hemi is like magically different that way, and it is a little bit. So let me talk more in depth about what we've been reacting to on these numbers. Let's look at what is the biggest difference between torque, not just peak, because the Hemi peaks way up here, but I think the biggest gap is right there at about 4,200 RPM, and it's from 525 to 467 pound-feet of torque. That's huge.
It's obscene.
That is really an obscene difference right there.
Wow.
So that's why we're saying that this 440 is just such a more killer street engine. I mean, it's making more than 500 pound-feet from 3,000 all the way up to 5,000 RPM. So right where you are snapping the converter and driving the car all of the time. That's really impressive. And also, just to put a point on it, the entire RPM range of the 440 is 3,000 up to 5,900. And we were able to run the Hemi all the way up to 6,500. So we're talking another 600 RPM with the same camshaft for 2 reasons. Smaller displacement, more airflow.
So now the question is, which one do you want to drive?
The 440.
What you do is you tow the Hemi car with the 440 in your motorhome.
That is what you do. And then you drag race your Hemi.
That's right.
This shows what has been my complaint about my Hemi all the time, which is it needs a ton of converter and it needs a ton of gear in order to run hard.
Didn't you tell me in your Super B you had something like a 513
I had 513
or something?
in it.
Yeah.
Right, and I put a
Takes a bunch of
373 in it and just knocked the guts out of the car. It went from 1060s to 1170s.
Wants to be up here.
Wow, this is kind of awesome.
I'm pretty happy.
It is kind of awesome.
I mean, you know, the 440 presented itself as a pretty good street engine, the 446 pack, and the Hemi, did what it was supposed to do. I mean, it was going to win the top end charge.
I really wonder if you took 2 identical cars to the drag strip, which one of these 2 engine combinations is faster if you were allowed to change the gear and optimize the package. I mean, does the Hemi have time to catch up with something leaving that hard and that well for the first half track?
Well, I'd say yes, because with the Hemi, you'd have a 5,000 RPM converter in it, right? If you're building like a stock eliminator or something where it's all-out drag car, 5,000 RPM converter in the thing.
There's more up there.
And if you did that with the 440, you would lose everything. It's
you'd want with the 440, you'd want to have a 35 or 3,800 RPM converter and get in the fat part of the torque curve to get the car to move quickly.
I think your rate of acceleration is going to be worse on the 440, though. It's not going to gain as many RPM per second.
That's possible. I mean, when you start up here with a lot of converter, you probably have the advantage.
Yeah.
Right. But in a basic street car application or a dual purpose vehicle, a 446 pack
440 is a killer.
Pretty tough.
In a street car, you almost have to pick the 440 because you've got a gear in it that you can actually drive. That's going to kill the Hemi, and the 440 is going to love it.
Yeah.
So from stoplight to stoplight, even the 440 is going to have an advantage.
And I suppose that there's people who can look at the episode and pick this apart and go, well, they're not 100% identical, but there's no way to make them 100% identical. They're completely different engines. The intakes are different, all that, but it's stock heads, stock bottom end, similar compression, identical camshaft.
Yeah.
And then arguably it's intake manifolds that you're just going to choose to run because they're cool, and they're both dual planes. So I'm going to say similar enough for me to actually go, wow.
Yeah, absolutely.
Yeah.
Fun stuff.
That is.
They did exactly what they're supposed to do.
I guess so. Yeah. But the more you start to think about it actually, rationally instead of emotionally, it does add up technically about the port size and the displacement and all those other things. It's doing what it should do. Huh. So final conclusions on this is, wow, the Hemi really likes to run at the top end because of the cylinder head. The 440's got more displacement and a much smaller head and makes much more killer torque, but rolls off sooner. And there's some technical reasons for that. The displacement and the cylinder head design.
conclusion is we got to run a Hemi.
We did get to run a Hemi, and we got to run a 446 pack, and we got to have fun and do cool stuff, which is what we do every time on Engine. Your valve springs and push rods could be costing you power and reliability, and you wouldn't even know it. Find out why this time on Engine Masters. This episode could answer questions that you didn't even know that you had. Here's the situation. In a pushrod engine, can push rods and valve springs affect power even in a situation where you don't have a valve float problem? That's what we're gonna find out. Here's the thing. Let's just look at the valve springs. You know, if you put a really heavy, beefy race-type valve spring in an engine, perhaps you've put a breaker bar in the front and you've turned it over and you're like, man, this takes a lot of power to rotate this engine. Does that mean that it kills power if you're running the engine with a stiffer spring? It must, because it takes, more work to turn it over. Second thing, you know that when you're setting up your valve train, you might have a push rod in there and a spring, and you're measuring lift. You know that valve spring flexes right there on the engine stand while you're testing it. But does that happen while the engine is running? And if so, how much power does it lose and what can you do about it? Those are the things we're gonna explore here, all with the help of the guys from Comp Cams. Let me start out by digging a little deeper into the tech of how this all works. Now, the valve spring is what we're really gonna be focusing on here in terms of how much pressure that puts in the system. Now, the other thing we're gonna be looking at is flex in the push rod right here. Note that I've intentionally done my artwork here so that the push rod is not directly in line with the lifter. You can see it's off like this to an angle a bit because that's how it is in a lot of engines, including this big block Ford. And the thing is, when that lifter is moving up and the rocker arm's over here and it's pushing at an angle, that rod can bend. And when it does, it's gonna reduce the lift at the valve because it's gonna take up that motion in here. The other thing that it can do is affect valve duration because as that thing bends, it's not imparting lift at the valve. Therefore, the lift at the valve is happening later and closing sooner, potentially, and we're gonna look at that in this also. Now that we've got all that covered, let's talk about valve springs and sort of how they're measured and how the pressures on them can be determined if they're light or if they're heavy. Let's imagine that this right here was the surface on the cylinder head where that valve spring is seated, right there. And then, I guess I'll draw a valve so that you get the picture of what I'm talking about. And then our spring is here. And then you've got a retainer up here, the thing that has like the little keepers in it and locks and things like that. So what we call installed height is the distance from right here, where the bottom of the spring is, to just to the underside of that retainer. That distance right there is installed height. And the thing is, when you get a spring straight out of the box, it can be really tall like this one right here. But when you install it, it's already been compressed a little bit, even when the valve isn't open. And typically you would see this at like, 200 to 100 on a big block. The big block Ford is unusual. It actually has an installed height of 1.880 inches. So we know that's our installed height and we can measure with a special tool what the pressure is on the spring at that installed height. The initial set of springs that we're going to run has 210 pounds. Now that's often called valve spring seat pressure. The thing is, it's not pressure, it's actually load. You'll get engineering strokes that'll tell you that's not pressure because pressure includes a unit of area, like pounds per square inch. It's actually load, and it is. It's 210 pounds, not PSI. Now the next thing that we're going to look at is, let's say we've got that same spring, but this time, this valve is open down here like this. So therefore, the spring has been compressed. And once again, right here, you've got the underside of the retainer, and right here, you've got where it's sitting on the cylinder head. You can see that it's been squished. Now, let's just say that it's been squished so much that the valve is at its peak lift, or what we call on the nose. That would be the maximum load that that spring is going to see, is when the valve is all the way open. In the case of the first set of springs we're gonna test on this thing, it has 550 pounds. Now let's talk about what we're going to go to. Here's real world examples of the parts that we're going to be using. This is the spring that's in the engine right now, and it runs perfectly. It doesn't float the valves or anything, and we're gonna install this. You can see that this spring is much taller. We're gonna have to squish it in here into that installed height of 1,880. And when we do, I can tell you that that seat load is no longer 210 pounds. It is 350. And when we've got the valve all the way open, the load is now 800 pounds. That is an increase of 45%. Now that's pressure that we don't actually need for this engine to operate properly, but it does answer the question, does adding that much spring pressure and that much drama in rolling the engine around actually affect power? That's what we're gonna get into. But that's not the only thing that we're gonna test. We're also going to look at that push rod flex that I described, how this thing can become a spring and get all bendy. And to do that, we're gonna run 2 different push rods with each of our different springs. I've got one push rod that is an 80 thousandths of an inch wall thickness. See, the push rod's basically a tube. It's hollow, you can see through it. And so the metal is 80 thousandths of an inch thick. The stiffer push rod that I've got is 135 thousandths, so this should have greater resistance to bending. It's also way heavier, but does that matter? These are all the things that we're gonna find out. This is gonna actually be super interesting. It's not something that you see tested very much, if at all. Steve Brule thought of this, and I think it's genius, and I can't wait to learn. We're gonna learn with this engine right here. This is a 514 cubic inch big block Ford. The key that you need to know here is that it does have a solid roller camshaft. Everything that we're testing here really should be reserved for solid rollers as far as the heavy spring pressures, because if you have a flat tappet cam, running way too much pressure like this can wipe out that surface from the lifter to the camshaft. And if you've got a hydraulic camshaft, too much pressure might cause issues with the little plunger and piston and valve that are inside the lifter. So this is solid roller territory, as we love on Engine Masters. All right, I'm gonna go talk to the Steves, and then we'll fire this thing up and find answers to all these crazy questions. All right, this is gonna be an interesting test that came straight from the mind of Brulé.
Ooh, that sounds interesting already.
Yeah, the whole valve spring thing. So our initial test with our 514 Ford is going to be with our light spring, which is 210 pounds on the seat and 550 open. And we've also got the thinner wall push rods in it, right?
85 wall.
So it is 85 wall, which would be 0.085 inches wall thickness on the push rods.
Baseline of Steve-O.
Well, that's the other question. Will we see the thinner push rod start to flex and lose power with the heavy spring?
2 or 3 or 4 questions that can be answered.
It's gonna be great.
Yeah.
One test at a time.
All right, fire it up, Steve.
All right.
We just made our very first test in the hunt to find out if heavy valve springs actually kill power, and also if flimsy push rods kill power. Right now, we've got the lightest of the 2 valve springs that we're gonna run and the flimsiest of the 2 push rods, and here are our power numbers. 659.9 pound-feet of torque at 4,500 RPM, and the horsepower is 648.9 up at 6,000 RPM. There's not much left to talk about. That's just is what it is.
It is what it is, and it's good.
So the next thing we're gonna do is run into the dyno cell and rip it apart and put in stiffer push rods. Right now they're 085 wall, and we're gonna put in 135. Yep. Ready?
I think it'll surprise you.
I hope so.
So here's a couple examples of the push rods. This is the older push rod we took out. Here's the new push rod. Visually, you can see absolutely nothing, but I can tell you, just feeling these, I can tell that this thicker wall push rod is actually heavier, so I know it's more substantial. And what we would see if we dissected it would be a smaller ID, which tells us that the wall thickness of the material is the same. It's the same material, basically an identical push rod, just a thicker wall. So it's basically a sturdier piece of pipe. So we've got the 135 wall push rods installed. Let's go see what kind of power it makes.
Look at our stiff push rod torque number, 660 pound-feet, and the horsepower, 652.6. I sort of desperately hope that the stiff push rods actually made a difference.
Me too.
Look at the overlay. Stiff push rods are in black, and flimsy ones are in red.
So it did.
Wow. It really made a difference up here.
You know, when I was looking at some of the data before I walked in, it looks to be about 5 up in that area. I mean, I was a little doubtful initially.
Yeah?
With this amount of spring, if that would be that big of a difference. And I think the real proof in the pudding will be is when we put that 800-pound spring on it.
Sure.
Because if that thinner push rod or weaker push rod is flexing and deflecting and losing lift,
Or
it's going to
breaking.
become more exaggerated with that bigger spring.
Wow, this actually makes me happy.
I know,
It's
me
better
too.
everywhere.
Because I didn't know if we were actually going to see anything.
No, it's better everywhere.
So I'm really anticipating these results being more radical when we go to the really stiff spring and the flimsy push rod, which is what we're about to do. Or should I say it's what Troy's about to do, because this is going to be a lot of work grunting this bar against a big, heavy valve spring.
Yeah.
Yep, let's go. Here's our process for changing valve springs with the cylinder head on the engine. First, we pull all the spark plugs. Troy's gonna put compressed air in the cylinder, just shop pressure, 100 pounds or something, and that is gonna hold the valves up so they don't fall in. Next, you'll see Steve install the tool on the stud for the rocker arm. He'll thread that on there, and once that is done, he's gonna start to squeeze it with the lever, and then you'll see him hold that fork down on the valve spring retainer and tap it with a hammer. There's the tap. Here's me removing the locks. 1, 2. And now the spring comes out. The new one goes in. All being very careful not to knock the valve down into the cylinder. You'll see when Steve puts the valve spring in and puts that fork back on the retainer, as he's squeezing it, he has to be really careful to get the hole in the retainer right over the valve so that he's not pushing on the valve, knocking it in the cylinder, which will release all the air pressure, and the valve will drop down in the cylinder, and it ruins our entire day. Here's our power with the 800-pound heavy springs and the Super Spaghetti push rods. 658.5 pound-feet of torque and 643.7 horsepower, which seems lower
Seems
than
lower.
it was before.
Only because it is lower.
Oh,
Show me it.
let's see.
Have a whole bunch of spring on it.
Oh, look at this. The red lines are the prior test that had the lighter springs and the heavier push rods. The black lines are what we just did with the beefy springs and the flimsy push rods. The thing you can't explain is this.
No, it's
what if the heavy spring is somehow
Controlling better?
controlling better down here and the push rod's not in distress yet?
Yeah.
And then the push rod starts to go away right here.
Oh.
And then makes more power up there.
What if the push rod's deflecting and not giving as much lift, raising low-end torque?
And duration if it is flexing.
Yeah.
That's a good one. That's way better than mine.
I am getting
That's
smarter
way
after all.
better than mine. You're right. Think of that. That was genius. What Dulcich is saying is that the push rod's bending, therefore reducing duration in the camshaft. And we know that reducing camshaft duration makes more low-end torque. And that's what's happening. That's genius, Dulcich. I love that when we come up with excuses that sound plausible.
No, you know, there's actually some merit to that. You know, the proof is going to be when we put the stiff push rod back in it, it should tilt the curve back the other way.
If that's in fact the problem.
Yeah.
But yeah, we lost a lot of power going this way. And to be clear, the reason we believe that we're losing power is because that push rod is flexing, giving up lift, giving up duration, and just making a mess of the whole thing.
Or is it because the spring is heavier and it's harder to turn?
Well, let's put in the heavier push rod.
Okay, yeah, we're not going to know really what we're knowing until we throw in the 135 wall push rods. And even then we might not know, but we can come up with excuses because it's what we do. No?
No.
Facts coming up on Engine Masters. Here we go. We just set this up for the final answer about whether valve spring tension has the potential to kill power. We've got our heavy-duty springs in this thing. We've also got our beefy push rods. I'm going to make Steve fire it up on the dyno, and we're going to have a look at the power. Here's our power, and actually it looks like we're going to conclude the stuff that we wanted to see. The torque with the heavy spring and the heavy push rod is 659, and don't forget the 0.9 pound-feet of torque, and the horsepower is 651.6. Let's look at the overlay of this, and it's got to be compared to the lighter spring with the stiffer push rod, which is the best power curve we've seen so far.
Heavy push rod.
Uh-oh. They're exactly the same. Yeah. There's a little bit of a something up there, but for all intents and purposes, the light spring and the heavy push rod and the heavy spring and the heavy push rod make the same power, the conclusion being that at least in this test, adding 45% more valve spring pressure over the nose does not affect the power curve.
I agree.
My whole interest switched gears as soon as I saw what the better push rod did, even with the other spring. It was like, okay, I wanted to go into this looking at valve springs. And you said, well, let's throw some push rods in there too, and let's do that. The guys at Comp loved that idea, doing both. And like I say, halfway through, I just went, oh my God, this isn't about the valve spring at all. This is about the push rod.
Well, but still, clearly, the whole thing about, you know, the engine turns over harder with a wrench when it's got heavier springs on it doesn't translate into any kind of a loss.
No, it does not.
Yeah. But the push rod, you know what we have to see? Let's look at a comparison of either one of these tests with the heavy spring with the light push rod. Yeah, look at that. This is a comparison in red of the stiff spring and the light push rod, and black is the stiff spring with the good push rod. And look at that, massive difference.
Yeah, I would have never caught that, honestly, between us guys. That whole thing about the push rod deflection causing the camshaft to actually be smaller.
Appear smaller.
And change something at the bottom, I wasn't prepared for that at all.
Yeah, I didn't see that coming either.
It's so repeatable, I'm very confident, and that's what's going on.
Yeah, and the reason Steve's saying that this is repeatable down here where the flimsier push rod makes more torque is because we saw it with both sets of springs, and it goes back to Dulcich's observation that the flexing push rod reduces duration.
It does tell me that the other spring is adequate.
Oh, yeah.
The 550-pound spring is adequate for this camshaft because we made the same power, same torque. It was identical. It was the push rod that was really significant in helping it pick up.
Let's talk about that in particular. we didn't need to add the stiffer valve spring to this, and there are in fact downsides to that, because you might be sitting there going, I might as well stack the biggest spring that I can get on my solid roller camshaft. There's no downside. There is. You're gonna wear out parts more. It's still gonna flex the push rod, and it's still gonna have rocker arm difficulties, like it's more strain on the rocker arm could break.
Yeah.
And the axle on the roller lifter.
I was just going to say the lifters. It's a higher strain on the lifter. So
And the seats. You can pound out the seats if you have a lot of closing load.
The valve seats. So while there are downsides to having too stiff of a spring, the question is there a downside to having too stiff of a push rod?
I'm not seeing that here.
No, not here. But I think a lot of people will have the question, well, the stiffer one is way heavier than the thin wall one. But does it matter over on that side of the rocker arm?
I think it's insignificant over on that side. I mean, that's kind of what we saw. This push rod is certainly heavier than the 85 wall or the 80 wall.
And I think that's all the notes that I've got. So our final conclusions are run the lightest spring you can that still controls your cam, but if you go too much on the spring, it's not gonna have an effect on power, and there's no downside to running the stiffest push rod you can. And we can also conclude that you really want to have stiff rocker arms and rocker arm studs, or above and beyond that, shaft rockers.
Right.
I like the shaft rockers. They're so much faster to adjust.
Yeah, there's a lot of betterness about shaft rockers.
Yeah, certainly is.
Yeah, what's a good test for shaft rockers? Could we actually get something with like 1,100 pounds over the nose and run it on a rocker stud versus a shaft rocker?
You know, when we talk about deflection, this has got a regular stud in it. If this had shaft rockers on it, would it pick up even a little more?
I'm not sure if we'd see that on this engine, but I think we could do it with something more hardcore.
Yeah, certainly.
And more hardcore is what I love. Anytime I can pull it off on Engine Masters. The thing you can't explain is this.
No, it's...
Oh, yeah, I can explain it if you want me to. Of course. Because the spring takes more power to turn the engine?
But the heavy spring's making more power right here.
I thought you said I was getting smarter.
Can you not snack in the middle of the tape?
Are you chewing?
Oh, God.
He just shoved that beef stick right down his throat, too.
In the city of Syracuse, under the sun, he solved the puzzles, every single one, with numbers spinning in his mind. A genius of the rarest kind. He yelled Eureka in the bath, found the secrets in every path, circles, levers, and the stars. Archimedes reaching far. He said, give me a place to stand, I'll move the world with just one hand. In every shape, in every flow, he found the way, he made it grow. Eureka! Let's go! He's spinning in circles, making it flow. He found the way, he made it clear. Archimedes, no one comes near. He lifts the world with just one hand. A genius born to understand. With every shape and every line, shining bright, it's Archie time. With geometry and pi in sight, he saw the world in perfect light. From volume to the golden crown, he cracked the code, he broke it down. He built machines that changed the game. His mind was bright, he earned his fame. With every thought and every plan, he's the smartest of all man. He said, give me a place to stand, I'll move the world with just one hand. In every shape, in every flow, he found the way, he made it grow. Eureka! Let's go! He's spinning the circles, making it flow. He found the way, he made it just one hand, a genius born to understand. With every shape and every line, he's shining bright, it's Archie time. He saw the stars, the seas, the air, found the answers everywhere. Through math and science he'd explore, a mind that always wanted more. Oh, full like energy. With every shape and every line, shining bright, it's Archie time. Eureka! Let's go! In the circles, making it flow. He found the way, he made it clear. Archimedes, no one comes near. He lifts the world with just one hand. A genius born to understand. With every shape and every line, he's shining bright, it's Archie time. Let's go!
The earliest superchargers in the aftermarket hot rodding world were centrifugal blowers stuffing air through carburetors, and nothing has changed today. As a matter of fact, I'd say it's more popular than ever, and you're seeing lots of people making way north of 1,000 horsepower blowing through a single 4-barrel carburetor. We've done it a bunch here at West Tech Performance, so we're gonna try and have a look at a whole bunch of different products and how they affect the carburetor itself as it's trying to deliver air and fuel. The other thing we're gonna do is investigate the problem that you may not even know that you have with your blow-through carbureted setup, and that is cylinder-to-cylinder distribution. We're gonna have O2 sensors here in every single header pipe, looking at the air-fuel ratio in each cylinder. Let's review that for just a moment. Under boost, we like to see fairly rich air-fuel ratios, sometimes around 11.5 to 1. You could be reading 11.5 to 1 in your single O2 sensor that you've got on one bank of your exhaust. But the truth is, you could have one cylinder that's all the way up at 16 to 1 and ready to melt and destroy itself, and you could have another one really rich at 10 to 1. You just don't know until you have sensors in every hole. Surprisingly enough, yes, these carburetor hats can affect that. So let me tell you what we're gonna do. I'm gonna run through and show you the 1, 2, 3, 4, 5 different hats that we've got here, and we're gonna run each one of them both straight down the carburetor as well as off at a 45-degree angle, because we've seen how that can affect the performance of the carburetor and how it delivers air and fuel to the engine. So, the very first one that we've got here is from CSU Carburetors, kind of a straight over and a straight down program, nothing real special there. Also very straightforward, the Pro Charger unit that has just a little bit more of a whoop-de-doo in it and also is a shorter height. Moving on to this extreme velocity, it looks very much like the Pro Charger unit, except voila! It's got a big spacer in it, dividing air so that when it's directly in line with the carburetor, it's attempting to even out the flow on the front 2 barrels and the rear 2 barrels. Then we've got this generic, what I'll call a shorty. It has a much lower height than the other ones, and we have seen that height is a big deal. Now the thing is, each one of these carburetor hats, oddly enough, won't fit the carburetor in a straight on sort of orientation because they hit right there on the float level adjuster screw. And so we've had to run a 1-inch spacer under each of these in that scenario. Same is true with this doohickey right here, which is made by Vortex/Paxton. I call it a UFO, and what it is a carburetor hat that goes on there that has sort of an air filter inside it, which is a diffuser. It looks a lot like a K&N air filter minus the cotton. It is just a screen in there, and the thought behind that is that it diffuses all those pressure spikes and strange airflow that might go across the carburetor and create problems. So we'll be testing that as well. So these 2 discharge tubes that you see right here are to accommodate the different orientations of the hats. And the one thing that you will notice on these is that they have a hole drilled in them, which is really unusual. You've seen it on past episodes. It is an organized boost leak. We're trying to keep the power on this engine down to the mid 700s because we don't want to go past 1,000 horsepower because we're pretty sure we're going to see some problems with the tune and run some very lean cylinders, and we don't want to go to the limit of horsepower and melt a piston out of our test engine. The test engine, you may ask, is this right here. First, let's talk about the fueling portion of it, which is the most important thing to what we're doing today. The carburetor is a Demon model that's designed specifically for blow-through supercharging. It's rated at 650 CFM, which would be sort of in normal conditions. Obviously, under boost, it's gonna flow a lot more than that. We know that it can make more than 1,000 horsepower because it's designed to flow that much fuel. On our fuel system, we are gonna be running a boost reference set up with our regulator. That's all from Automotive. The fuel that we're using on this whole test is Sunoco 116 octane. So I think the first thing that we're gonna do is get it on the dyno, and you're not even gonna see a naturally aspirated test here. We're gonna be boosting everything with that ProCharger F1A94, and we're gonna start off with what we believe to be the best scenario, which is the CSU hat plumbed absolutely in line with the carburetor, just like that. All right, you ready for this? Let's go. This is gonna be something.
Yeah.
Yeah.
I'm not sure, well, I think I am sure what.
I think we're going to see the extremes, maybe.
I hope so.
I mean, is it only there, really, guys, to connect the supercharger to the carburetor? To physically connect it, and that's all there is to it?
No, there's a whole lot more to it than that. And I think
sure?
that's where
Yeah.
David and I came up with this originally, was back when the boxes were popular.
That's what I used.
We started using boxes because these were so bad.
Yeah.
And we could put something on at a 45-degree angle, it'd misfire. You could actually rotate the hat and hear the misfire at part throttle go away
Yeah.
and rotate it and come back. And they would just do all kinds of crazy things. It seems like they're a little more squared away now. They've got some height things and a lot of that stuff squared away. But we have some oldies and some newbies,
And we'll find out. Okay, fire it up. Let's go with what we presume to be the best one, which is the taller 90-degree kind of one that we've run a few times, and we know that this baseline's actually gonna work. And after that, we'll just mow through them and find out what goes wrong.
all right, let's go.
Goodbye, CSU. Hello, ProCharger. UFO doesn't cut it.
No, it's not that good.
I'll bet you anything it's a boost restriction because of the diffuser in there. I bet it reads less boost than the manifold than the others.
Probably.
Yeah. Before we start talking about all of these, can we just look at why that one lost power and sort of take it out of the mix? Because I think it is a boost problem.
I think we can relate it to boost pretty accurately.
Yeah, totally.
Wow.
Yeah, that's
Yeah,
where it's
what
at.
we're seeing there is that diffuser inside what I'm calling the UFO is just a boost restriction. And so clearly we could pull it up and get back there and make the power. So the question is, does it actually diffuse and have better distribution than all the others?
Does it?
Does it? So what we're gonna do here to sort out which one of these hats we like the most is not look at the horsepower because they're all very similar. Instead, we're going to look at how the carburetor reacted to each one of them and how it delivered fuel and air to each of the cylinders in the engine. We're gonna find out if any of them created any radical lean cylinders, which is our main concern for killing parts. Before we get to comparing here, let me tell you what we're looking at. This is a graph of all 8 cylinders in the engine and what the air-fuel ratio is in each one of them. So all the way at the top, they're also labeled here. We've got cylinder number 4, and it's the leanest one, which is almost 13.5 to 1 at the peak. All the way down here, you can see this particular cylinder actually crosses over. I think that one's number 2-ish. And it starts really, really fat, and then it gets leaner and hangs on leaner. And so we're able to look at this whole graph to see, is there one cylinder that's just way off the plot either direction, or are they all really spread apart? And our main interest here is up there at the higher RPM, higher boost, higher load, that there aren't any that are going into the danger zone, which I think for this deal we would call, you know, we don't like 13.5 to 1, but anything worse than that's really bad.
Well, and again, part of that depends on the amount of boost and for how long.
Yeah, how long is a big part of it.
Big part of it.
So between those two, which would be the CSU hat in black and the Pro Charger one in red, I think I'm gonna give the very slight edge to the CSU.
Yeah, I'm gonna say very slight just because it's down just a touch.
Yeah. Pretty
close.
It's pretty close. I mean, it's a tie.
Yeah,
really.
Because, you know, I think if we go back and look at the overall average air-fuel ratio of these two, the CSU could be slightly 2 or 3 tenths richer than the Pro Charger hat.
You could see that.
The only thing that influenced me, I think, was this one cylinder, honestly. And they're the same. It's not bad.
It's got a couple over here. But
yeah,
you know, things are not, at this power level at wide open, it's not going to be at 3,900 RPM very long, or 4,000 RPM.
Yeah, so neither one of these is bad, but I am going to take Pro Charger out, and currently the CSU is in the lead, but by
very close.
By a shrug. Okay, red is the extreme velocity, which, as a reminder, is the one with the split in it.
Wow, the CSU.
And black is the CSU, and once again, that's clearly going to the CSU. Extreme velocity hits the bench.
Yeah, that one was a lot more definite as far as you could see that spread
at a glance. So the CSU is currently our winner by a fraction. We're going to compare it with the little short guy. Ah, look at that.
The CSU wins again then.
The red here is the shorty and the black is the CSU.
You know, maybe a couple right in here, tiny bit of difference. I'm really surprised that short one did so well.
Ultimately, as far as how it would affect your life in the car, I would not concern myself with running any of these in the configuration that we had earlier today, right?
For fun, let's take the CSU against the UFO.
Okay, now we're going into the one that's different than these regular hats. We're going to compare our best one, which is the CSU, to what's on there now, the UFO with the diffuser in it. And
that's a blowout.
CSU wins again.
That's a blowout.
A lot.
Yeah.
And you know, originally I think that hat was designed to help this problem.
And
to
when
stop
you and
doing
I
different
tested
things.
it 20 years ago, it was way better.
Yeah.
But I think back then, we probably had the really short one on there with no spacer.
Yeah, and I remember some of those things that we would have to do to get it there. We would go all the way around the outside and come in the side of the hats and things.
We did that.
We did not have good entry angle into the carburetor.
And I'll tell you what we were comparing it with. It wasn't a hat at all. It was the full carburetor enclosure.
Okay.
Remember that? Old school Paxton enclosure, and the UFO was better than that. So next round is going to be the 4 carburetor hats at an angle to the carburetor with no spacer on them. This could get ugly. Now we're switching to those crooked hats. They're going to be at 45 degrees, maybe this way. I don't know what Troy's got figured out here, but we're also going to remove this spacer right here, which we think was helping all of those hats, because the taller that they are, the more you've got to turn and the air is going to go down the carburetor instead of across the top of it. So we're going to take this away now. So that's going to be 2 strikes against these hats. They're going to be both crooked and short.
Well, when I went in to just kind of warm it up and do a test run, I noticed that the air-fuel ratio was considerably leaner than it was when we ran it with the hat heading straight in. So I kind of stopped midway in the run, not wanting to damage anything, and it looks like it's almost a full ratio leaner than it was.
Just by taking the same hat from straight to crooked.
Yeah, just by moving it that much, we've leaned it up about a ratio. So just as a matter of a comfort level, even though we said, no, let's not jet it, let's just move it, I feel like we really need to go ahead and add some fuel to it just as a safety measure to get it down into kind of a safe range.
So you're just going to toss some jet in the secondary?
Yeah, I'm just going to throw a half a
richer.
dozen in the rear, make it safe, and then we
Yeah.
can proceed on.
One thing I'm already noticing, though, is look how much tighter the grouping is.
I know.
Yeah.
It's crazy. Look at this versus that.
And who would have thought? I would have thought going straight in would be the
Yeah.
best, but, you know, so far, we're seeing a much tighter group.
Well, we'll know more once we jet it.
Once we jet, that might change.
Yep.
Yeah.
Okay.
We just ran all of the angled carburetor hats, and we sat here for 45 minutes amongst ourselves, just nitpicking that spaghetti. All of this gobbledygook and figuring out the cylinder distribution. We didn't want to bore you with the excruciating details, but I think we can actually wrap it up. We decided that the worst was this guy.
Yeah.
Why?
Extreme velocity with the divider. And it wasn't so bad when it was on the carburetor straight, but when we angled it, that divider is kind of crossing over between a right front primary and
Yeah.
a left rear secondary, and it just does some horrible stuff in there.
We saw on that one, I think, a really good lesson, which is there was a bunch of cylinders that were tight together and really rich, and then two that were really lean. And the point about what happens if you've got
Well-
one O2 sensor averaging all of them.
It's a tuning nightmare because the weight of your average is going to be those rich cylinders, and those two outliers that are already super lean are going to go meltdown mode.
Yeah, completely. Next one that was, I don't know, fairly ungood was the real short one when we ran it sideways and took the spacer out. What happened there?
We had one cylinder that was kind of the same thing. It wasn't
Yep.
as bad as this, but look, what's the difference whether you blow it up with one piston or two?
Yeah.
I like that.
Yeah.
I'm going to make a T-shirt with that. How about all of them? Just roll the dice. Okay, so I think we're deciding that of those of us in this group, we're not using either one of these guys, right?
That one's out.
Yeah, too much of a risk. So we came down to the nitty-gritty looking at the data between the ProCharger guy and the CSU one. And it was really, really close.
Yeah.
We
Yeah.
had to pick it to death, but ultimately, CSU
I
rises to
think
the
so,
top.
slightly.
Yeah, just ever so slightly. Honestly, either one of these is just fine with me. Not that any of them are particularly good. My bottom line is still, if you're gonna do something like this, just get sequential EFI. It's gonna make your life so much better.
There are places for it, but you know, there are some guys who are just so uncomfortable with the EFI. This might get them by because it does
Yep.
get pretty decent up in the higher RPM ranges. Maybe okay for drag racing, bad for Bonneville.
Yeah.
You know, just
And the other thing is I just absolutely lied to you because if Steve and I were sitting around at Roadkill Garage and I'm like, dude, let's throw a ProCharger on my 440.
We would just throw it on.
Yeah.
That's all we would do.
Yeah, we'd probably use it with a thermoquad.
Yeah.
So we would not practice what we preach. But if you're trying to make this power level, I think you should. Okay, so we've looked at a lot of data. We've done a lot of bench racing, and I want to get into final conclusions of what we figured out here because in truth, this didn't come out nearly as badly as I hoped.
They all worked.
They did.
Bottom line.
Yeah, and I will say in our prior testing from all of us, it's been more frustrating than we saw today. We have seen stuff that won't even run.
yeah, misfires. You can change the orientation of the hat, and it actually will go in and out of misfire by rotating the hat while the engine's running. I mean, we've seen some pretty ugly stuff.
Yeah, and so this is a peachier situation than we saw today than normal. So let's go through my list. I think number one, when they were all aligned straight with the carburetor, we nitpicked some differences, but they're all the same, really.
Pretty decent.
Yeah. I mean, they're pretty decent. They're equal amounts of bad and equal amounts of good.
Yeah.
I would still choose either the Pro Charger or the CSU.
I agree.
The UFO, we didn't give that a fair shake, I think, because it's just sort of in a different category. It was such a boost restriction that it killed so much power. And the distribution was not awesome with it, but you could throw a pulley at it and make just as much power as with the other ones.
Agreed.
Yeah, and it was also restricted with a smaller inlet than everything else we ran.
And that's probably the reason I might not use it in the future, is that this is a 3.5-er, right?
Right.
And the UFO has a 3-inch hole in it. Next conclusion, and I think this is really the biggie for you at home in the episode, is that carburetor hats do behave differently depending on how they're oriented on the carburetor. So if you've got a good tune-up and you've been drag racing for years and you're like, this is no problem, and next thing you know, you go to a different setup and your distributor's in the way and you're forward and you angle your thing a little bit differently, you could be a full ratio out of whack.
We saw it. We
Yeah.
saw it today. Had to go back and put some fuel in the secondary because it changed big.
Yeah. And that is a massive takeaway from this, is that it really can make a difference. As a matter of fact, if you all of a sudden are cruising at the dyno and you've got your nice happy CSU on it with a 1-inch spacer, and next thing you know, you're home going, oof, it doesn't fit my hood. I'm gonna get the little short guy with no spacer. Once again, you could be stumbling into absolute disaster.
It all matters.
Yeah, it all matters. And to quote Brulé, I had to write it down.
Really?
Yeah, it was genius. At higher power levels, you just can't take things for granted. Get to the dyno with any of this stuff if you expect to save your engine.
That's all you can do.
Yeah. Speaking of saving your engine, you know what I think would make all of these way better? I'd put a 150 shot under all of these, put a nitrous plate under the carburetor,
Yeah.
and I am betting you, no joke, that it will improve this whole scenario.
Look, I'm with you on the nitrous every time.
Right. No, but think about it. We've tested nitrous on dual planes. It improves the distribution. It's forcing fuel down those holes. It's got the fog of nitrous. It's drawing it all together. It's cooling it down. I really think it would be an improvement. And I'm not prepared to do that today, but you know what I am prepared for? Throwing a ton more boost at this to find out, does the carburetor get better or worse when we make 1,000 horsepower?
How did I know you were going there?
Have you seen this show? I have an idea. Let's from now on make every episode 1,000+ horsepower. It'd put me in a way better mood.
It's easy to do.
It is unfortunately super easy to do these days.
Yeah, and a lot of fun.
And it takes your naturally aspirated 318s out of the picture, which makes Steve happy. All is well with the world, as it is every single time on
Engine Master.